என் தம்பி யூடியூப்ல பாரு.
சார் குட் மார்னிங் சார். Sir, good morning, sir.
Good morning.
Yes,
Very
we
good
welcome you,
morning.
sir.
Very good morning. Good morning. Okay, thank you. Thank you very much. Sir is joined. Correspondent
No,
is
sir.
joined. Okay. I think
Okay.
sir will come. Okay.
Sir, good morning, sir. Sir, kindly
Good
unmute,
morning,
sir.
eh? Good
Yes,
morning.
sir. We welcome you,
Good
sir.
morning, good morning, good morning. Thank you. Hello, good morning, sir. Hello, good morning, sir. Hello.
Hello, good morning. Srinivasan here. Could you hear me?
Yes, sir. Hearing, sir. Hello.
Fine.
Senthil, sir.
Yes, sir.
Sir, kindly ask Kanakpriya ma'am, sir. Okay.
Shall we start the session, sir?
Yes, sir.
Yes,
Yes.
sir.
Okay, sir.
Is all the participants okay, sir? Shall we start the session now?
Yes, sir.
Yeah, sir. I will just start sharing the screen.
Sir, a pleasant good morning to one and all gathered here. Every day may not be good, but there is something good in every day. Yes, we are all here together for the live webinar series of recent trends in engineering for space and defense. On behalf of Arul Murugan College of Engineering, Karur, Department of Electronics and Communication Engineering. First of all, I humbly welcome Dr. P.V. Kandasamy sir, correspondent, Arul Murugan Institution, who is striving hard to lead and take the institution to the greater height. I welcome you, sir.
Thank you. Thank
I
you.
feel honored in welcoming Dr. P. Shanmugam, sir, principal of our institution. I welcome you, sir. Now, I cordially welcome our today's resource person, Mr. R. Srinivasan, sir, scientist DRDO Delhi, who has presented himself for us in spite of his busy schedule. I welcome you, sir.
Thank you very much.
I also extend my warm welcome to department HODs, faculty members, and other participants for this live session. Now, I request Dr. P.V. Kandasamy, sir, correspondent, Arul Murugan Institution, to deliver the presidential address. Please, sir.
Good morning, sirs. I am Dr. P.V. Kandaswamy, correspondent of our institutions. I extend a warm welcome to Mr. Srinivasan, the scientist from DRDO. It's a really proud moment for us, sir. I am extremely thankful to you for having accepted this session. Really, because the DRDO is contributing a lot in our nation's safety and development. Of course, a resource person from the premier institution of premier knowledge hub of the nation is now here to talk about the recent trends in defense and space, which will definitely inspire the participants like students or faculty members. Definitely they will get inspired and they will try to work in this field in the near future. And of course, everyone believes that the nation's safety is in your hands only. So I'm very thankful to you, sir, for having accepted this offer. Thank you very much once again. Thank you, sir.
Welcome, sir.
I request the participants
Thank you, sir, for your speech.
Yeah, thank you very much.
Before the session starts, I would like to introduce about our honorable chief guest, Mr. R. Srinivasan, sir, who has started his career as trainee assistant engineer in Birlas, and in 2000 he joined with the Defense Research and Development Organization as scientist, and also he is pursuing doctorate in vibration signal processing in National Institute of Technology. He also received DRDO Performance Excellence Award. We are happy to have such a wonderful and eminent speaker and ready to share his knowledge with us. I extend my best wishes to all participants to use this webinar and get maximum benefits for career development. I hand over the session to Mr. Srinivasan, sir. Thank you, sir.
You're welcome.
Can you take over the session, sir?
Yeah, sure. Good morning, everybody. And especially morning, sir, Dr. Kandaswamy and Mrs. Kanagapriya. Thank you very much for giving me the opportunity
Thank you.
myself in this podium regarding the recent trends in engineering for space defense.
Thank you, sir.
Yeah. So basically, one second, let me go with my presentations. Yeah. When I was supposed to give a presentation on the topic of recent trends for space and defense, and to be honest to myself and to all of you, that I'm not so great in engineering or technology and all these things. We are just working on one of the few areas what exactly the nation is in need, and we are trying to do our best with all the constraints what is we are facing with respect to the technology, the availability of materials, and the resources. And even in this, what we are trying to do now, I have gone to a place like I am standing in the shore of an ocean, and I'm trying to just see that how wide and how dense it is and how deep it is. I'm just able to appreciate with the inputs what we are receiving from the people who have gone deep into that or who have been interacting with us, who have told their stories, and they have shared their experience. I'm trying to share it among all of you. And a few of the droplets, what I could feel, that I'm just trying to share it, and it is a big ocean. So what I'm going to present today is only a jinx of what I have heard and what I have learned over the years and what I have been working during this period. And I hope these inputs will be of a bit of use to all of you, all the participants here, and for the faculties, for the students, and for other industrial personalities who are available. And so with this, let us start the seminar on recent trends in engineering for space and defense. Morning to all of you. And today, as such, I'm so happy and honored to collect and what I could perceive that what is happening in industry and what is happening with the technology and engineering today. As many of our batchmates, a lot of professionals are there and a lot of new generations have come, they are working and they have a lot of ideas and a lot of inventions have happened over the years. But generally, all of us, we know that this of heritage. Science many questions really amuses us and it fascinates all of us. But the engineering is what that we feel is what changes the world. As an engineer, we need not give you a perfect solution for every problem what we are facing today. Rather, what I feel is there are a lot of problems available in this world and the technologies are available. But the question remains is that are we providing solutions for everything and anything in this world? But what I personally perceive and feel is that we did not give a perfect solution for everything, every problems in this world. But what we are expected is to give the best possible solution and the shortest time available so that the community is comfortable and they are able to work on it. And with this, I welcome all those students who are graduating this year and they want to graduate in the coming years to the fascinating world of this engineering. And every day is going to be an interviewing day for all of us. The output is not as expected what we look for. The future is always uncertain because the changes are happening every day. And the expectations also changes and the goalposts are shifting. And we have to be content with what we are developing, what we are providing. And every day we have to look for the new things, what we can do better. That's how the engineering starts. So with this, let us see that what basically the engineering is. If you look at the Aggregation Board of Engineering and Technology, engineering is the process of defining a system that we have a lot of subsystems, a lot of components available, or a lot of raw materials, and the philosophies are available. So engineering becomes the process of devising a system, a component, or a process that what do you call that process control or the process assets to meet the desired needs. And basically, it boils down to the decision-making process where we normally iteratively and repeatedly look for a solution. We find the problems and we find another solution. You try to make it more better, in which the basic sciences, the mathematics, and the techniques, what we have been evolved over the years, that has been applied to convert the basic resources to be the stated objective or the required result for the common good of the community. This is what basically the Accreditation Board of Engineering and Technology is what is defining the engineering is. And in this here, in my presentation throughout, due to my profession and the data available and the technicalities and the other acts, what I am presenting in this seminar or the webinar is mostly taken from the open resources, and I'm giving credit to all those who have given me the inputs for making this webinar presentation, stated or not stated otherwise. And so let us go further. So if we talk about engineering, so engineering is not a new field that what we are looking at. It has been since the evolution of our humans. The process might have started when the humanity came into existence, maybe somewhere in the Stone Age, or before that, almost some 10 lakh years back, 1 million years back, when the humanity came into existence, the engineering started. Every human, they wanted to make their life a bit easier, and they have devised a tool for that, and they know how to use that tool also. Right from the beginning, if you see, the fundamental tools had been the wheel, the pulley, and the lever. So these three things, we never know that when it was invented, and normally that's why we make a statement normally when we are doing some design or something here, don't reinvent the wheel. We don't know who invented the wheel and how he could think of the process of inventing a wheel. And subsequently, if you see that in the recent times, the engineering, it has evolved with the evaluation of the civilization. Also, it has got modified, it has become more precise, and it has become more requirement-friendly or user-friendly. Like you might have seen that the ziggurats of the Mesopotamia, where we have seen a lot of civilizations, initial civilizations have come up. And subsequently, the pharaohs of the Alexandria in Egypt, where we have the pyramids, which the construction is a marvelous one. And in our area, if you see the cities of Indus Valley civilization around 3000 and 1700 before Christian era, that is on the banks of Indus River, where the agriculture and aquaculture was the major industry. And they had the planter cities, they had the residential buildings, they had the colony, they have the walkways, and they have the missionaries to do that job. So a lot of things were happening, and there were things, technicalities were evolved, and the people were making the available resources to be useful to the common good of the community, for their work to be easier and to get the maximum output possible. So if you define this, engineering had been there since the evolution of our humanity, I believe. Rather, okay, one question I'm keeping it for the later discussion on the webinar. We have our greatest epics of our time, that the Ramayana and the Mahabharata. A lot of discussions are going on whether these two events actually happened, or these events, it's only a fiction story as somebody has written. Whatever be the case, either it may be a great fiction from the greatest minds, or it may be a technologically advanced society during those periods. Whatever be the case, there were the events described, and those events really makes us feel that, yeah, there was something available, there were some technologies available, and there were some engineering things were happening, and the people could make things work to the way what they wanted, and they were better than what we are today. Maybe a fiction, or maybe the event actually happened. There were things that we will keep it for the further discussions at the end of this seminar. It may be for thought-provoking one day. So let us go to the next. So in our place where we are regularly visiting, if you see, okay, I belong to the place Tanjavur in Tamil Nadu, and I have been frequently visiting the place called the Bhavishwara temple in Tanjavur. Everybody might have visited who are all participating here, and they might have really gone through the massive structures, the big area, the compound walls and everything. And we have been, in the childhood, we have been playing through those areas. And mostly we used to visit that temple for the bhakti reason. But subsequently, as we grow up, as I have grown up personally, and when we frequently visit on the vacations and other things, I feel that quite a few questions, and we might have a lot of inputs which is flowing around in our social networking sites and other data we are frequently receiving in WhatsApp and Facebook and all, how the Brihadishwara temple was made, and how that 80 ton of stone was carried to the top of the building, why there is no mortar is used, and how the structure has been conceived, and what is the bottom dia of the structure, and what is the top dimension of the structure, and subsequently how they would have calculated. And recently people have made the plan and elevation of the Brihadishwara temple. I strongly could not believe or understand that without a plan or the elevation drawings or the basic idea, they would not have built these sort of temples. Not only this Brihadishwara temple, you can go around all places in Tamil Nadu, in India, it is every place temple, and there is some massive structures available. You go to Rajasthan temples, in the right side you can see there is a giant temple, and similarly the plan and elevation of that temple is given here. But the question what it's exclaiming me is the technicalities of these constructions, how this question is still remaining, how they would have definitely made it all these structures, and still that long time standing, with this time tested, the structures are available. So the few photos what I have taken from the open resources. This is Abu Dalwara temple in Rajasthan. Quite a few occasions we have visited this temple when I was posted in Rajasthan, in Chittor. And there is another giant temple is the right side what you can see. The intricacies of those sculptures, the intricacies of those items, and if you see the parallelism in this structure and how it held the load-bearing factors and all these things, if you see, possibly I wonder that how the artisans would have been those times. Today, if you see that we have a lot of tools and the computing machines available, we can see quite a few weapons, what we are seeing for the Indus Valley civilizations, what has been dig out, and the traditional measuring scales. What recently, what I have seen in one of the online videos that it has been made of plastic, and they are using it for measuring the corners of buildings recently. The traditional measuring tool which has been there in our civilization for so many years, so many centuries as such. And the firearms made of the bronze for the last almost 300 years back. These things are readily available. So if you see that today we have a lot of tools and the computing machines to carry out the calculations and to provide the models. Today we have to make the drawing or a 3D model, we have softwares like AutoCAD, the SolidWorks, the ProE, and the StatPro for calculation of our architecture and civil constructions for the estimations for the surveys, and lot many more software available. So that's why we look at the temples and the structures in ancient India. In this case, if you see, that raises furthermore questions about the mind that what tools they would have used to make all these things, because today we are talking about high strength steel tools for machining, for drilling holes and for the different materials. But they have the what you call the rocks and other things what they have used for the constructions, the strength had been very high for this. And today we are not able to make a hole in a granite slab where we have to spend each whatever the high speed steel drilling bit what we are using today. We are not able to make a hole when we are constructing a system, and we have to go for a special tools for that. And every slab for every hole, normally high speed tool, we have to break one. But those times with the granite structures, they have gone for their sculptures, they have gone for making intricate joints and other things. Really, I keep wondering that what are the tools they might have used. If the tools are to be made, how the technicians know that this tool is to be used for this purpose and this way only. And this really brings another question that if there is a tool available, you know there is a way how to use it, then who had taught this? What was the curriculum and how was the training session was there? How the skill was developed in those years? So there are a lot of questions which keeps accumulating when you look at all the structures and all those materials, the firearms of 300, 400 years back. So definitely engineering mind which had been working and there a curriculum to teach the young generation and to bring it for the work, they make it employable. And the employment, they had the sincerity and they had the patience to make all these things. These questions, when you put them all together, it raises a question that how it was done earlier, like a great monolithic structures made of a single stone, or the transportation mechanisms, the selection of the raw materials, and assembly of the smaller sections. These things, it's what creates an interest in engineering, and it gives a way for us to take it further forward. If we go further, and definitely I believe that one life is not enough to understand what engineering was applied earlier and where we are today. We have been moving towards the digitization and the digital techniques and connectivity and all those things. Possibly they also might have had all these things. But the only thing what differs is that we are not able to understand that what they had. Possibly the work is still on. People are trying to dig and know that how things have been working earlier, so that many of these fewer points can be used in our present day technology also. So this knowledge we might have lost it over the years, either it's our aid and self-destructive, or because of the destruction during the war period or the aftermath of the war, whatever the case it may be. We need a lot of time, we need a lot of energy to dig into all those things to know further how it happens, how it can be used. In the recent times, to start with, we have Sir Vishwesvaraya was the greatest mind what we had in India. With that, we had during those period, we had Jagdish Chandra Bose who were working on botany, and Satyendranath Bose who worked with Dr. Einstein on this relativity theory and subsequently and the rest of the things. And we had Srimati A. Lata, who was the first lady engineer in India. And of course, you know, being the our alumina factor, Dr. Srinivasa Ramanujam, who belongs to Tom Higher Secondary School in Kumbakonam. And in the recent times, for the 3 areas of atomic space and defense, we have Dr. Homi Bhabha for the atomic and Dr. Satish Dhawan for the space, who is the father of our fluid dynamics, and Dr. APJ Abdul Kalam, who is known as the missile man of India, who has taken DRDO a different height. And in the local social level, we have Dr. Varghese Kurian, who was the revolutionary man for the White Revolution of India, and Mr. Fakir Chand Kohli, who is generally known as the Bhishma of Indian software, who 1969 around, who started the Tata consultancy services along with Tata's group. And in this case, with all of the great minds of our Indian scientific forum and our forefathers in engineering and technology, and India is definitely in the forefront of innovation in the recent times. Our 37 Indian scientists from the 9 great institutions were part of the discovery of the gravitational waves, which was the biggest project worldwide, intergovernmental and interdisciplinary project. And they have received the Physics Nobel Prize in 2017. And also the discovery of the neutron star merger at Laser Interferometer Gravitational Wave Observatory Laboratory, LIGO. We have one office in Delhi also. And basically it is there in USA-based company, and many of our Indians have been involved in that LIGO Observatory. Subsequently, in the defense area, we have the development of the BrahMos, and intergovernmental organization between the government of India and the government of Russia, that is Brahmaputra and the Moscow River. The name has come from that, the BrahMos. And the advanced air defense supersonic interceptor missiles, which has been recently tested, and the diverse missile and rocket systems, which has been frequently tested around and being deployed for the users, that is service sectors, Air Force, Naval, and Army. And we have the remotely piloted vehicles for survey and rest of the things, and the light combat aircraft, which have been of a lot of news around for the LCAs, which has been inducted, and quite a few things are being exported also. So these are the few examples of India's progress in strategic and defense technologies. And we have very credible capability in the way of space technology. Of course, we know that we have launch vehicles, GSLV and PSLV, where we were able to launch hundreds of satellites. 104 satellites was the maximum recently done. And we have the Chandrayaan missions and the Mars orbiter missions. So these are the things where India is in the forefront of innovation, and we are making it happen, and the things are happening. And if you compare the Indian Space Research Organization, where the motto of ISRO had been to harness the space technology for the national development while pursuing a space science research and plan to the explanation, we have a lot of other countries, the leading countries, the Russia's Roscosmos, and of course we know the NASA of USA. Then the ESA is the European Space Association of 24 countries put together. They have formed an association in Europe. And we have the China's National Science Academy. And in the defense area, we have the Defense R&D Organization, which is working on a lot of recent technologies and futuristic technologies for our defensive services. And the PLA Academy of Military Science of China, who is working in this defense area. And the Defense Advanced Research Projects and Agency of USA, the Israeli Aerospace Industries, Elbit Systems, and the Rafael of Israel. And the Russian Foundation for Advanced Research Projects, and the UK's Defense Research Agency. These are the few agencies who are working both in space and defense area. So let's go that in the last 1 year and getting into the criticalities and what is happening around in this world during this during these years of defense and space area. In the past year, we had 2 major traction in the global space sector from both the government and the private sectors. 2 major conferences had in Europe recently highlighted the trends in the new space. One is the New Space Europe in Luxembourg, and the Space Tech Expo in Bremen, Germany. It showcased some of the future and the latest technological trends in the space of and the satellite market. Now, the thing is that the space sector is getting more and more interesting and challenging because of new space applications, because we have the newer communication system requirements, satellite, Internet of Things. Earlier, now we are talking about the Internet of Things within our close community, but now it has come to a satellite, the Internet of Things. The geospatial solutions where we are looking at locations and the time management and the time synchronization and all, and the real-time tracking, the social engineering like our prediction of flood, the prediction of earthquakes, earthquake management, and disaster management, these sort of things. And a lot of things are there, and many areas where this space sector is coming into the picture. And as per the Quilty research of Europe, it says that they normally doing the research on the satellite and the space industry. According to Quilty Research, currently there are more than 10 companies that are entering into the satellite IoT market because it seems that it is going to be the next biggest market in the world, that is satellite IoT. And it is going to be a game changer in the satellite communication industry in the years to come. But in Europe, the satellite constellation is sufficiently peaks for 2009 with the numerous launches of Starlink and Condor satellites. The low Earth satellites like the LEOs, low Earth orbit satellites, the business has become more attractive to capture that satellite broadband customers. According to that Euro Consultants forecast, almost 8,500 small satellites weighing around 2 tons, it has to be launched around in the year 2028, of which almost 42% of the market will be driven by the communication satellites only. So the future falls in small geolocks. The future almost falls in that small geo-based satellites. It really looks very promising, and the operators are thriving on the existing infrastructure. And the need of the hour is how we are going to improve the infrastructure, both for the onboard space requirements and the ground requirements. So if you look at it, the total space engineering, it consists of 3 major areas. So one is the spacecraft, what is going to be, or the payloads, what is going to be put onto the space, be it a defense or in the space area. In the space area, it is going to be the satellites, or maybe for the deep space, the payload for the defense requirements. And the second one is the ground support systems, where it comes around the ground requirements of the control, communications, information, and other things. The third one is the launch platform. And we will go only one in the subsequent discussions. So if you look at the space engineering for payload, mostly in the space engineering, we are looking at only the satellites for the Earth applications or the rovers for the deep space, which has a great level of intricacies in design and development. With the time, what's happening is the satellites are getting smaller to suit the present day requirements. And we discussed earlier the exponential developments of developments in the component level, because the components are getting miniaturized day by day with the semiconductor technology, and it drives the design to be the compact payloads. The increased utilization factor of the launch vehicles, the payloads are to be of a less weight and to be of the smaller size. If you look at the 1 or 4 satellites, whatever ISRO has launched, many of the satellites are nano satellites. So mostly has come from the colleges or universities, or from the private sectors, or maybe from the hobbies also. So with the advent of the electronics, the semiconductor technology, what is available today, everything is getting a bit smaller, and it has become more weight-wise, efficiency-wise. Everything is really better now. So we are able to launch a number of satellites, and that is the need also. And the third factor, what comes into the commercial requirement, is the cost. It plays a very crucial role in the space market. The reduced cost will definitely witness an increase the satellite constellation capacity. Now we are working on GBP, that is gigabits per second. It will make us to terabits per second linkages. And there is a need also for this, because as the number of users are rapidly increasing. Earlier, there was a time where we had the smartphones and other things were less. Now everybody and every individual is having a smartphone, and almost all the jobs, everything is done through the smartphones, through the smart applications, whatever is there available for each phone. So this calls for a lot of data, a lot of communication network, and a lot of data handling systems and data mining systems. So these satellites, as we all know, used by public authorities for the social and administrative purpose also, whether be it is in the defense purpose, or subsequently for the defense intelligence and other areas, or subsequently for the regular administration, like I said, the disaster management and crop tracking and these sort of things. There may be commercial communications also for that. So next on to the ground, if the downstream data acquisition, if you see, the payload also, if you, before going to the ground requirements, if you go about the payload requirements, if you take up the defense applications, the warheads, we have the conventional warheads and we have the non-conventional warheads. These are to be delivered at the designated designation rather, and the range can be a short range missiles to the intercontinental ballistic missiles. And those missiles have to be the passive or the active seeker mode it has to work upon. So with all these things, what is happening is that the payload of the space engineering, there is a wide variety, and there are a lot of areas where you have to work, And R&D is happening in almost all the areas wherever it is happening. Only the requirement that we are limited by the technology today. So the work is happening both in the technology, the basic science of that, and subsequently in the engineering part of it, where those technologies, whatever is available already, and what is going to come up maybe in another 2 years and 3 years, how it can be integrated onto the future visions and make it work, and how it can be better utilized. The third one is the requirement is that the quick assembly and the deployment is the need of the hour. Like for the defense and other areas that you have to be prepared all the time. You don't have any lead time for the preparation of the payloads or these things, and subsequently the time is reducing. You have to assemble it very quickly. So we have to make it a much modular things. How modular packages and modular systems can be made and how it can be utilized for the engineering of modulation, modular components. These things are really, people are working on that, and it is one of the brightest area in the future. And the next, getting onto the space engineering ground support systems. The flashy areas are the data acquisitions through the satellite systems, and subsequently how to store the data. And we made with so much of people around, so much data around how we are going to, and the analysis and taking a logical decisions based on the data what we have and analyzing those data. And subsequently, the integrated defense mechanism, not only I'm talking about the defense area, the integrated defense mechanism comes to the safety and the security of the data what we have, and how to access it and how to control the access also. And subsequently, the communication and the control of the decisions or the outputs of our analysis and consulting. So if you see broadly, the data exploitation, the market trends in the data exploitation is mostly in the machine learning and artificial intelligence, the cloud computing, and the data fusion. These are very common areas where we are seeing, and there is no area where this machine learning and the AI has left. So ultimately, we have to see is that the smaller, self-sufficient, and simpler solutions is what we have to look for. It has to cater to the need of the localized society, where the problems are different for each localization, and we have to give you solutions for this, where we have to take the global data and solve for the localized solutions. And the second thing is the internetworking of those smaller societies to form a bigger one, and so that overall applications are generated and overall engineering provides a solution for the global scenario. These are the two things. But what actually happening is we are trying, the knife is falling, and we are trying to catch the knife, catch the falling knife. If we get hurt, there is a different issue. But how to deal with this, the data security, the privacy, and the utilization of the data. How far we can do and how not, we should not do all these things. Ultimately, the same technology, you have to provide the answers that we will go on by one further. And the third area, which is the more fascinating area, is the launch vehicles. The space flight is undoubtedly the remarkable and probably the most audacious human achievement of the 20th century. The launch vehicles, earlier we were talking about the smaller vehicles which can travel up to 20 kilometers, 30 kilometers. You can very well go to the site. There is Richard Naka's sites for this propellant and all these things. Anybody and everybody can just go and view this. It has started as a hobby, how the propellant can be used. And in our initial conditions, the Tipu Sultan era, we had the rockets available where metallic tube was filled with chemical propellants, which was fired against the British Army. These sort of things, which started as a hobby and which is as a crude method, over the years, it has developed into a highly controlled and highly precise launch mechanisms. So there are a lot of technologies. What we are using is the escape propulsion, where we are trying to escape the Earth gravitational force that is from the Earth surface to the orbit where we want to intend to reach, and the in-space propulsion that is in the orbit where we want to go and how it has to be propelled, or for the deep space propulsion, so from the orbit to the outer space. At about 65 kilometers, we have the re-entry point. The atmospheric is almost closing at 65 kilometers of the Earth surface. And the time we are getting out of this Earth surface, or we are trying to enter into the Earth surface, we have a lot of criticalities. Those criticalities what are being attended to. And we have the missiles or the rockets of different ranges. And we have the different weapons also, whether it is a ballistic weapons or it is a tactical weapon. The ballistic weapon follows parabolic path, and the tactical weapon, we have the maneuvering things, which calls for a lot of controls. And these are the major things that the launch vehicles are designed for different purposes, and each design and the requirement changes with the applications, whether you want to go for to escape the Earth's gravitational force, or you want to come back to the target, or you want to go for the deep space propulsion. And we have in ISRO, we have a lot of vehicles right from the beginning, SLV-3 to the present GSLV Mark 3. A lot of developments have happened right from the liquid propulsion system, the solid propulsion systems, and subsequently the cryogenic propulsion systems. And subsequently, we have the hybrid propulsion system. Of late, recently, people are working on plasma propulsion systems and the electric or magnetic propulsion systems. And we go by one. The solid propulsion system, if you say, it is mainly the solid propulsion systems are very heavy, and they are mainly used for the boosters for the initial stages. And this gives a lot of thrust to the weight, and so improve the thrust at the initial takeoff time, where we have to escape the gravitational force the solid propulsions are used. Earlier, we are working on the liquid propulsions. Now we'll see it in the later slides. So the solid propulsion system has an advantage of it's a highly reliable system which has been worked out and standardized over the last 30, 40 years. So the reliability is really very high. It has been very robust and it is very powerful. And safety-wise, if you compare whatever we have today, safety-wise, it is of better perspective, and the ease of use is really good. And the preparation time for the solid propulsion systems is a bit short compared to other systems, and the construction is also very simple, though it is technologically highly advanced. For the people who are already working, the construction is a bit simple, so that things can be taken up easily. But the major disadvantages for the solid propulsion system is that its efficiency is less because it is very bulky, and this cannot be controlled. Once ignited, it has to complete the ignition, and you cannot switch it off in between. You cannot control the ignition part of it. Only you have to use the flame output to your requirements. And the thing is that with the recent additives and other things, it is highly explosive in nature. Unless if you miss out something in the safety precautions, I said the improved safety. There are a lot of safety things have been taken up in the solid propulsion area, but if you miss out something, it is highly explosive in nature. So present today, if you see the solid propulsion system, normally in the right side figure, we can see we have that the green color, what is showing that the propellant grain. Normally, the propellant grain is made of ammonium perchlorate, alumina powder, and hydroxyl terminated polybutadiene. That is for the binding agent. This generally forms the major constituent of the solid propellant. Normally, it is cast onto the motor casing, and the motor casing is being cured to take the shape of that, and so that the igniter at the head and side, if you see, the head and side can be used to initiate the propellant, and once it starts burning, the total flame under the pressure of say 30 bar or 70 bar or 100 bar, whatever it has been designed for, it escapes through the nozzle which is on the tail end side, the nozzle exit cone. You can see that. The basic physics works here. When there is a high pressure plume is expanded out of a nozzle, it gives a energy in the other side where the object is moved forward. This is what the basic philosophy of any propulsion system. And there is a nozzle throat which there is a convergent, and where it is expanding, the nozzle exit cone. When high pressure plume is exiting through this, the vehicle takes off and it moves forward. So to protect the temperature not reaching the outer motor casing, we have the internal insulation either made of rubber materials, which is bonded onto the metallic cases, the motor case. And to control the direction of the forward movement, we have the thrust vector control or thrust vector actuators, where the nozzle can be moved to deflect the flame direction, so that the direction of the flight vehicle can be changed. Or we have multiple nozzles, where each nozzle can be used for the vector control, or we have other different control systems for thrust vector control, which can be applied onto the motor, so that the flight vehicle can be controlled. So if you see at the solid propulsion motor under the nozzle, generally the motor casing is made of emerging steel to that. We have moved to presently the carbon epoxy composite is what is being used worldwide, and a lot of work is happening in the composite area also. And in the rubber lining for the insulation, earlier the rubbers were used, and now the EPDMs are used. And the propellant, we are moving to high energy RDX based propellants, which can give the higher specific impulse and more burn rate, so that the energy available is more, so that the power ratio can be increased. The propellants of the increased hazardous levels, people are working it out. The RDX based propellants is one area where the technology is working, where the scientists are working now. And the thing is that all this RDX based propellant or the more hazardous level propellant, we are able to achieve in the lab level of 10 kgs, 5 kgs, and 20 kgs. But when it need to bring it to the actual utilization, that has to be worked on tons, maybe 2 tons, or 15 tons, 20 tons, and 30 tons in this level. So the processing technology for handling this RDX-based propellants, high energy propellants, the safety intricacies, and subsequently the engineering part of it, the equipments for handling those, mixing, casting, curing, and NDT part of that. A lot of things are there in there. And the testing part of this high energy propellants, also a lot of engineering people are working, but only thing is that when it comes to the biggest level, there is a lot of challenges in attending this. That is one major area where we have to work it out. And secondly, the requirement of any propulsion system is that we have to keep the weight less. If you reduce the density, the weight will come down. So suppose if you take the managing steel, the density is around 8.1. And if you work out the carbon epoxy composite, this comes out to almost 1.4, 1.5, even around 2. So when the density reduces, obviously the weight reduces, it gives you the weight power ratio will be better for you to handle. And when we are looking at the high strength materials, these are the one area where already the work is on, and there is a lot of scope for further work to be carried out. Similarly, what we are looking at for that silicophenolic or the carbon-carbon composites for the nozzles and the rest of the things for the jet vanes. In the right side, you can see. These are the things where the material, basic people are working on materials actually. This material technology, we have to change how to process those materials, how to take it for the production level, in the mass scale, how it can be made, so that it can be utilized for further utilization in actual launches and actual space missions or defense missions. Like I said, that the control mechanisms can be either of the flex nozzle or nozzle systems, or we have divert attitude control system where multiple nozzles are kept, where things are already on. And in 1 or 2 missions already in US, it has been used. And we can see the jet vanes. So we can go through the material and open source available or the textbooks, what is already available in the solid propulsion systems, like our Saturn's book or any other book, where the basic idea had been given. But and the technology behind this has also been explained. But what exactly the work has to be done is that how this can be used in present day scenario with the available material or with the futuristic materials, how the efficiency can be improved and how the more precise control can happen. And in the flex nozzle systems, there is a lot of other areas. What is happening is that the sensing and the feedback mechanisms for the mission control. And the recent area in the control system, we have the Hutch Infinity control system where people are working. This is one better area where we can spend some time and work on it. It is going to be the futuristic control system. And if you look at that SAB in Belgium, they have developed one 11-ton electromechanical actuators, because normally the electro-hydraulic actuation systems are used for the nozzle control, or the electromechanical actuators are used. If you see, look at these two things. The thing is that the electro-hydraulic systems has been used for so many years. Now they are getting replaced with the electromechanical actuation systems. Earlier we had the limitations in building the BLDC motors of electromechanical actuators has been made by Sharka Belgium. This is the highest rated electromechanical actuators which has been used in a Vega launch vehicle of US, which has substituted the ring. And if you look at the hydraulic systems, say this one point we have to confirm, I'm not very clear. 5,000 PSI is what is used for mobilizing cars. What happens is beyond the 5,000, the material beyond the 5,000 PSI, what the material required, the requirement totally changes. And we are not gaining anything for its power to weight ratio. That is why the limit of 5,000 PSI has come. Already we are working at 2,000 PSI and all in most of the space and the different areas. So these limitations, handling of those hydraulic systems, integrated power packs, the system has become more complex in hydraulic. So people have moved from electro-hydraulic systems to mechanical actuators. But in electromechanical actuators, the problem is with the BLDC motors and the servo valves and these things. So a lot of work is already on, and it's already identified. People have innovated, and these things are being used. This 11 ton, we have to take it to 20 ton of electromechanical actuators, so that heavy lift vehicles can use this 20 ton electromechanical actuators. This is one area in the solid propulsion systems. And subsequently moving on to the liquid propulsion system. This liquid propulsion system, if you see, basically, though in the initial period it was used as a main booster, subsequently the liquid propulsion is used only as a control mechanism. Because one major advantage with the liquid propulsion system is it is controllable on demand. Whenever there is a requirement, you can fire one servo valve, make the oxygen and the fuel to feed through the line. It can go to the nozzle, it can mix together, and the fuel and oxidizer is mixing, it burns, and subsequently it gives a thrust. So switching on and the switching off facility is possible with this liquid propulsion system. And generally, this liquid propulsion system is used for orbit injection or the trajectory control of the missiles and the rockets and the space vehicles. So what is the problem in this? The problem with the liquid propulsion system is that the fuel and the oxygen has to be kept in a separate chambers. What you can see here, it should not mix, because the time it mixes, it starts burning. So handling this fuel and the oxygen separately is the biggest problem. It is a highly corrosive and highly dangerous material for the fuel and oxygen this chambers are. And you need high pressure chambers inside the launch vehicle, where air pneumatic system was compressed to almost 200, 300, 400 hours, and it is kept in a tank, and subsequently it is used for feeding the fuel and oxygen into the nozzle throats. And the complex engineering and routing for these mechanisms, the material needed to hold this highly corrosive raw materials is what the major issues with the liquid propulsion system. But still, even today, we are using a liquid propulsion system for orbit injections and the trajectory control and the fine-tuning roll controls and roll pitch and yaw control, and subsequently for orbit injections, giving an incremental velocity to the vehicle. These we are using. The third one, recently what people are working in this area is ion and plasma propulsion systems. If you, in between, before this ion and the plasma propulsion system, we have a hybrid propulsion system where it's a combination of the solid and liquid propulsion system. But here the major problem is that it is difficult to achieve the major thrust area. We are not able to achieve a very large thrust with this sort of hybrid propellants. So these hybrid propellants are very rarely used, and we are moving towards the ion and plasma propulsion systems. So earlier, whatever we have seen, all are the chemical propulsion systems. But when it is come to now, it is a non-chemical side of the propulsion system. We have the plasma. The high exhaust velocity of the propellant, it's more efficient for the long distance interplanetary space missions compared to the conventional counterparts. What exactly we are looking for is that this ion propulsion, it's one of the impulse what we can get through this ion and the plasma propulsion system is of low impulse also we can get it, so that the incremental changes at delta, what we are looking in the velocity of the vehicle, that can be achieved because with this ion and plasma propulsion system. This is highly suitable for small attitude correction and small roll correction or the pitch and yaw corrections. What is happening is that the propellant injection, that the electrons are emitted by a hollow cathode, which is at the head end side of this propellant, and subsequently we have a tube which can separate the electrons and the ions. The electrons are ejected and the ions are exiting because of the acceleration by the grid. It moves out of the nozzle at a very high velocity, and this velocity of the particle movement, this again the basic law that it propels the object to the forward directions. But once the ions are out of this nozzle, we have to inject the electrons out of that nozzle exit to neutralize the ion beam which is coming out. This system had been very critical, and this thing, and still R&D is going on in this area. Similarly, subsequently, we have other areas other than this ion and the plasma propulsion. The futuristic propulsion systems, we have the solar cells available. Basically, it is a solar panel what we are going to use. Recently, one manned flight mission has manned aerospace. One flight has been flown with only solar panels in the wings. And the tether propulsion is that we are trying to use the magnetic philosophy available in the Earth's surface or any other moon's surface. That magnetic field, a wire will be there, and that magnetic field interface with this wire, and it creates a magnetic current. This current can be used for propelling the object. These are all very lightweight objects which can be doing it. Third one is the aero capture, where the gravitational force of the moon or the Earth or other planets are used to brake or to slow down the aircraft. And here, basically, what is happening is the kinetic energy is converted into the thermal energy, and subsequently, the thermal energy is used for the control. The third major area which is not left out is the nuclear. There is a fusion energy. The fusion reaction, it occurs between the two atoms of hydrogen collides to create a helium-4 atom. that releases the energy. This is what basically the fusion is. That energy of helium-4 atom, the enormous energy what it is releasing, can be ejected from the engine to provide the thrust. But basically theoretically what it says is that what presently we are taking about 7 to 8 months to reach the Mars, we will be able to reach it in 3 months. That is the level of energy what is going to give. Again, a lot of intricacies are there in that, using the fusion energy, including the safety point of it. So the laser propulsion is one thing where it is a totally different concept. Now presently, if you see whether it is a liquid or solid or plasma or nuclear, we have the object and the energy is available in the same system, where there is an object in which the object is to be propelled, the propulsion system is inside it. But in the laser propulsion, it is a beam powered propulsion systems where the energy source is located in the remote area, maybe possibly the ground base, or at sometimes in the future it may come in the space based also. And this laser energy what is provided through these laser systems onto the object, it will propel the object into the forward direction or to the direction wherever it is required. And the last but not the least is the nuclear propulsion. Everybody knows about the nuclear reactions. But a major question arises that how to use these nuclear things. It cannot be used in our Earth surface because of the safety and other precautions, what everybody knows, we know. So it has to be used in the outer space. The nuclear thermal rockets, they are going to be the high thrust propulsion systems. But how to use it, how better it can be used, and how to achieve this, these are the one areas where we need a lot of intergovernmental and there are a lot of policy decisions have to be taken. And if not today, sometime it will come up and we'll be able to use it for all our missions. With all these things, we have a lot of propulsion systems which are taking the payload onto the space and it is being launched and it is being put onto the orbit or for other defense purposes. But what about the reusable launch vehicle? Recently, our Indian Space Research Organization, ISRO, has conducted one test on reusable launch vehicle. The basic motor casing, that is the booster casing, once it takes all the systems and it returns to the orbit, it becomes useless. It is being jettisoned and discarded. Why the same motor casing cannot be retrieved again? Because anyway it is falling onto the Earth. Why it can't be retrieved again and reused for this purpose? The major advantage of this thing is the cost effectiveness. Once you make a casing, this can be used for the multiple times and it reduces the cost of the total launch vehicle. This has already been done twice in US and the commercial space agency, they have used it. And the basic test one, the ground test has been conducted by our ISRO and in the near future, it will be used in full-fledged launch mechanisms. So if we take about the payload and the ground support systems and subsequently the launching mechanisms, launch platforms. The launch platforms, not only it is only the propulsion, there are a lot of avionics systems which are inside the launch computers. And when we are talking about the avionics systems, we have to be more precise, the major parts of the launch avionics systems is going to be the onboard computers, the vehicle controllers for all the electromechanical and electro-hydraulic actuation systems, then the power supply systems, the batteries inside the launch vehicle, and the communication systems to convey the data about the status of the launch vehicle onto the ground and for further control. And the telemetry and the transponder systems to get the data about the healthiness of the vehicle or the tracking of the vehicle, what is being launched. Then in the defense area, we have the active and passive seekers and the altimeters for the measurement of the height and close to the navigation and the positioning systems. Basically, to conceive all these major components of your flight vehicle, the major areas are the system engineering and the simulation is the first thing where you take up the mission, you go for the system engineering, how to make that launch vehicle, and subsequently simulate it on ground. The simulation on ground, we have using the present day computers, normally a simulation takes almost 7 to 10 days to run one single simulation. But with the advent of our launch vehicles and other things, like we are talking about subsonic and supersonic launch vehicles, and now we are moving on to the hypersonic launch vehicles. The hypersonic launch vehicles and the multiple time re-entry onto the Earth's atmosphere, these sort of things, presently the direct numerical simulation techniques are coming, where earlier in the estimation and simulation, normally you take your propulsion model, and we are taking about the wind model and subsequently the temperature model of the launch vehicle, then the atmospheric model, aerodynamic model of your shape and everything, the materials. All these things are put together, and the simulation is made that how this flight vehicle is going to behave when it is being used. Now with the advent of supersonic and hypersonic requirements, what things is that the present day system will take months together to give a result. So we are going for a direct numerical simulations. Secondly, the model whatever we apply in making these simulations or based on a lot of assumptions, and we make a lot of approximations out of this, where the accuracy nowadays is a requirement and a lot of systems are coming in. So we have to be more accurate. So the assumptions are getting reduced, a lot of equations are to be sorted out and they have to be solved to make it a highly comprehensive and composite solution for before we take the vehicle for engineering and fabrication and subsequently realizations. And the third one is that the electronic hardware design per se. So once the total system is developed based on the system engineering and the individual subcomponents are distributed, the designing of our individual electronic hardwares and the review of those designs and the reliability studies of those individual subsystems and the algorithms, what it is going to embed onto that, and the software for those things, and the software validation and the software. Then once the hardware is made, once the system is about to fly, before that we have to go for the hardware in-loop simulation on ground, how the mission is going to behave as if there is a ground test, what we do. Then the individual subsystems ought to be subjected to the environmental tests to make it more ruggedized so that it can be clearly and confidently used for the flight applications. And the integrated ground test of all these systems, other than hardware in-loop simulation test, we have to go for a lot of ground tests for propulsion, for control, and for the payloads. So these are the major areas of a avionics system works, and it is not what do you call that over the night we cannot do rest of the things. As I said earlier, that these flight systems and flight vehicles and launch mechanisms, either it is for the space or being for the defense, we have to be first time right. We don't have a second chance to say that the systems can be repaired and can be flown again or used again. So this first time approach is what is the bottom line when you work on the system engineering or in hardware design or in software simulations or the ground tests. So whatever the mistake, if you make one of the few parameters, if you make it is going to be very costly. And if you look at the first block diagram for the systems, that we have the mode selectors, the trajectory generations, and subsequently the guidance laws and the guidance principles. Then the autopilot has to be done, that how the mission will be taking care of the control systems. Subsequently, to execute the autopilot commands, we have the actuators, we have the propulsion systems, and the airframe body of the flight vehicle, and the sensors to give the feedback for the mode selection, subsequently for the guidance and the autopilot. And if you look at any of basic missile, we have the missile seekers, whether it is a seeking missile or non-seeking missile. We have the seeker or signal processing systems. And subsequently, we have line of sight communications, then the guidance launch and command system implemented, then autopilot and airframe and propulsions. These are the basic areas. So in the avionics systems, when we go for the electronics of the avionics systems, we have different systems, whether it is an onboard computer or it is a navigation system or the controllers or the seekers and subsequently the antenna for everything. The criticality, what we are facing nowadays is that most of the components are imported. And once we are importing it, then the standards, what is applicable to those components, whether like normal industry level components will not work. We have to go for military grade or space grade components. Once the components we receive and we select the components, we have to go for the certification of those components for further use, and the screening of those selected components has to be carried out. And the third major problem is the availability of those components from the international market, and the lead time to get those things is what the major bottlenecks what we are facing today. And we have the best expertise to create the architecture. The architecture depends on the application actually for which we are going to use it. Are we going to use it for the onboard computer, or you are going to use it for your controller? You have to go for the FPGA, or you have to depend on the DSP boards, or you have to design a new architecture with available systems, or you have to design your own SOCs. All these things depends on the particular application where we are going to work. And the second thing is the QA standard of these particular components, the build-grade components and the specified components, with the availability of that. You will look for some fancy items that this I have to use it, but if it is not available in the market, so that the component selection plays another important role. And once you make the component selections and preparing the gerbers and making the PCBs, the density of the PCB nowadays is going up to 22, 24 layers. And we have to use that surface mount components under the BGAs what we are using, and for the requirement, many occasions, many systems are being designed with system on chip, which is defined specifically for that purpose. And above all, if the systems are already available, there is a requirement like 2 functions or 3 functions can be clubbed onto one single system, and a single package can be made. So the requirement is that the volume that the component it occupies inside the flight vehicle that can be reduced, and the cable harness, the wiring and the rest of the things can be reduced. That long path wiring will not be there. We can come onto a single system. With this requirement, when it is improving with the advent of the improvement in the PCBs and design into the components, the connectors, earlier connectors were big, it was very bulky. Nowadays, we have got high density connectors, and we have different type of connectors like a D-sub or circle connectors, lock-on connectors, and umbilical connectors, snap-off connectors. So a lot of connectors are coming, a lot of signals are required, and basically what is happening is that development or improvement in one area, it gives a chain effect in rest of the areas, and everybody we have to work on different areas to make a complete system, and one change made one place, it is going to affect the furthest end of the other phase. The chaos theory definitely works here. Next requirement, what we are facing in the avionics systems on the system is that now, earlier we had the RF circuit separately, we had the analog circuit separately, the digital circuit separately. Now the system is not so. We have to work on the mixed signals. There are signals which is coming in digital, there are signals which is coming in analog, because the whole world is analog even today. But what we are working is digital. So the thing is that you need to have the analog transducers where you have to work on the analog signals. Even the commands are to be given in analog in many of the occasions. The actual execution, it happens in analog, and that is more precise also. So the mixed signal processing is another challenge where we are working, and the processor's capability, there is no limit to that. The expectations are very high, and the electronics is also improving. So high-end processors to meet the data update rate, like INS data and the initial navigation system, what we are using, GPS and all, we are trying to update at every 20 milliseconds, 10 milliseconds, 5 milliseconds. Even there are requirements that time has to be updated in nanoseconds for many of the applications that we will see later. And the high operating frequency to meet the control demand is one thing. And the next requirement is that, as I said, that since we are using it in a flight vehicle, the architecture has to be such a way that it has to be fault tolerant, and it should be have a redundant architecture. Like even if the one system fails, the second system should be able to take up the job and should be able to deliver. That is one thing. And being the high density build-grade connectors are coming out, the isolation and the EMI EMC requirements and the EMI EMC problems are also increasing. So the basic design of the PCBs, the wiring, and what do you call the component selections to be compatible with the EMI-EMC requirements. These are all rising very high, and these are one major areas where we can, things are already, people are working, and the bands are increasing, right from gigahertz to 14 to 42 to 78, we are moving as such. And the ruggedized and qualified for the flight applications is one area, the quality assurance and the ruggedization principles, how to perceive what is going to happen in the flight when it is flying, and how to simulate those conditions onto the ground and get the units cleared. This is one area where that like vibration, the shock, what is going to experience, or the accelerations and the, what do you call that, environmental conditions like the temperatures. These are one area that how to perceive what is going to, how to decide that what is going on, is going to experience in the flight, and how to simulate it on ground, and what is mostly required, and what is minimum, and what the maximum not to stress. These are the areas already for the avionics systems where things are going on now. And secondly, for that talking about the telemetry systems, we've been talking about the sensors and the telemetry systems. The MEMS-based sensors, of course, everybody knows that they are already in use. And I know the next technology what these people are working is nanotechnology. It is in the offing. And the nanotechnology, the common trait is the size, where the size of the material we are working it is in nanometers. And these are the one area that we will see it in the next slide. The nanotechnology is the next area where already work is on, and we are getting materials also. And the sensors have to be self-conditioned sensors, because memory-based sensors, self-conditioned sensors, these are the one area where it can remember what is happening, and physiological implications can be taken. And third thing is that structurally embedded sensors, where now we are mounting few sensors on some of the structures, trying to measure the characteristics of the sensors or something, where the requirement has come that the sensors will be embedded onto the structure itself, or the system something available, characteristics available in the structure itself can be taken as a reference to know the condition of the structures of the sensors. And of course, the wireless sensors. The self-conditioned sensors and the wireless sensors are already being used in industries, and not now. For the last 20-25 years, we are using these self-conditioned sensors and wireless sensors in the industries. But what the requirement is how to use these things in flight vehicles, where the available volume is constrained, the weight to power ratio is limited, and the requirements are more. Number of sensors are going to be more. Normally, thousands of sensors are mounted onto the bodies of the flight vehicle when you are going for a developmental trials to collect as much information as possible when the mission is flying. So the generally telemetry systems, we have a input transducers are there. Subsequently, there is a signal conditioner and there is an encoder. This encoding philosophy is a basic encoding philosophy like pulse code modulation or QPSK or APSK, these sort of things. And subsequently, we have the FM transmitters modulated onto the FM, and the FM transmitters are for long. And we have the antennas. We are using like the conformal antennas or the printed PCB antennas. Now, the recent work is going on in the antenna side also for the wraparound antennas, where the total antenna is wrapped around the vehicle itself, and that wrapped around the metal can take care of all the possible frequencies which is required for the mission, irrespective of whether it is in K band or KU band or Ka band or in C band or H band. The single antenna, high bandwidth antenna, how it can be used for all the purpose. This is one area where there is work going on. And similarly, when the vision is transmitted from the flight vehicle, then normally we are receiving it on the ground receivers. Then whatever the encoding mechanism has been used, the same decoder has to be used here. Similarly, and the data is processed in the process to give the valuable. The data is converted into the information and given to the designers back. If you see, look at these things, how the technologies things are that the Ethernet we are using for the last 15-20 years, more than that, and as per the IEEE 802.3, we are using it. But initially, the Ethernet was available only at 10 megabits per second. But today, the same Ethernet is available at 1 terabits per second. So if you look at the basic protocol, things are available, and only the major changes are coming is the how it is being utilized. So the engineering part comes into picture, and the better utilization of the same protocols, same technology, what is available already, how it can be better utilized, which is what we are deciding, and that is the need of the hour also. How better we can use the available technology to give the best output. And if you look at the material side, otherwise for the telemetry and the communications from the flight vehicles, when there is a re-entry philosophy is happening when the things are coming back. The thing is that we have the plasma effect or the ionization happening when the vehicle is entering into the atmosphere at a height of almost 60 by 70 kilometers height. So there is always a disturbance because of the plasma effect. The telemetry data will not come onto the ground and will not be able to receive it. Now the work is on that how this can be defeated. Whether it is at 65 kilometers or 70 kilometers, if there is a lag on the data or there is a loss of the data, whether we can store the data and send it again when we are coming out of this plasma effect, or any other material which can defeat this plasma effect, which the ionization can be controlled. Like there are some methods like spraying of water molecules or sort of molecules where the ionization can be reduced. Similarly, the technology of data communications, the materials, the antenna areas, the encoding technologies, and the band in which we are operating, and how the system can be made smaller, compact systems, how the functionality can be integrated onto a single unit. These are the major areas the work is already going on. And third one is the navigation systems. If you look at the navigation system is what gives you the position. We have the gyroscopes, we have the accelerometers available. Based on the accelerometers and the gyros, it exactly calculates and tells you the accelerometers will give the acceleration of the object. From there you start integrating and you get the position. And similarly, the gyros, it gives there is a reference frame. From the reference frame how much we are moving back and forth. That gives the input about the attitude of the flight vehicle. So right from the earlier times, the mechanical gimbal-based gyros were used. Subsequently, RLG, that is ring laser gyros, and FOGs, fiber optic gyros, are being used now, and MEMS-based gyroscopes are already available in the market, and which is being vehemently used for major applications. Coming into the future one, the hemispherical resonant gyroscope was in the research area, and already there is a claim that one European agency has suddenly developed it. Possibly it will be used in one of the missions. And in the future area, we have that cold atom interferometry and nuclear magnetic resonance gyros are the two areas where very serious R&D is going on. The cold atom interferometry, the basic requirement of the navigation system, when it comes to that, is the what you call that accuracy is what the major thing, and the drift has to be less. There should be a stabilization, and the warm-up time should be less, and the accuracy has to be more precise. With the increasing demand by the day by day, so we need more accurate and positioning systems. Nowadays, everybody is happening. So in the financial market you take, or the delivery market, or the tracking systems, or the telecom networking and the power plant management, everywhere if you see that we are looking at, as I said earlier, 10 nanosecond is what the accuracy what people are looking for. With this timing accuracy, the navigation system is going to be the major changes it is going to see in the next future. So I think we have spent almost more than 1 hour in this avionics itself and engineering. So let us quickly go through the seeker systems. For the defense applications, if you see, where earlier we discussed about seeking or non-seeking missiles. There are two types of seekers, where imaging infrared seekers are there, and radio frequency seekers are there, either in mmW range or other different ranges. The major thrust area in these two areas are that how the imaging has to happen, and how it has to be transmitted onto the ground for further decision making. And as the vehicle is moving, the velocity of the vehicle is very high. The time available to make the image and to take a decision is very less. So accordingly, the sensors, the domes, and the electronics have to be made for those things. So disruptive countermeasures are already available for both infrared seekers and the RF seekers. So the identification of the right target and keeping the cone angle of the seeker to that area, and the antenna position for the control of using those servos, these are the major areas where we have to work on, and these are mostly electromechanical systems, and the gyroscopes are coming into play in this. So if we compare the RF sensor and the IR sensors, we have predominantly the RF sensors are active, where we are spending some waves and we are getting the feedback out. But for the IR sensors, mostly it is in the passive operation. So both RF sensors, IR sensors has got the countermeasures available in the world today. The range wise, if you see, the RF sensors are more better compared to the IR sensors. But target imaging, if you see, the IR sensors are more simple, and we get a better target for that. So the lot of advantages are there in RF sensors and IR sensors, and work is already on, and a lot of improvements are coming out. It gives a lot of scope in working on imaging systems, both with RF and IR. In the communication and data, like I said earlier, so we have a DTH televisions, we have single source point to multiple destinations. These sort of things are the requirements. Already in the inter-satellite communication systems, there is effort to work on the optical communication between the satellites, like the European data relay systems. So optical communications and normal RF communications for the Earth observation data, and high platform stations for the non-space based data. And these are the one major areas where things are happening, like a normal communication, what happens today with the common people. The same thing are being used in technical areas also, but the only difference is the requirements are totally different, the specifications are totally different, and we have to develop the hardware and the methodology for to satisfy the needs of that requirements. Then in circuit designs, earlier we are normally working with the circuit designs. Now the quantum computers have come, which can do the calculations based on the probabilities and the potential to process the exponentially more data compared to the last the classical computers. The quantum computers are one thing. As I said earlier, the mixed signal ASIC building blocks is the another major area where we are looking at. And the third one, if you look at the productive circuitry for EMI, EMC, and the spot shielding techniques are the one area where there is a lot of work is going on, and a lot of efforts are also required to consume different techniques of confirming to that and the testing part also. And the development of the IP core for individual subsystems based on your specifications requirements and for the SOCs. These are the one where we are looking for. And once everything is working, you need a power supply for that. It mostly boils down to the electrochemistry of that. So presently we are going for primary reserve batteries or the secondary batteries, what we call the silver oxide zinc or lithium ion batteries, or if you look at the silver oxide zinc batteries and the lithium ion batteries, what we are looking at. Lithium ion batteries are normally not used in spacecrafts only because of the safety reasons. Other than that, there is nothing. So, but the current R&D activities are happening in sodium ion batteries and lithium sulfur batteries. These two things, the improvement is looking for because of that fast charging, long duration, multiple charging systems, and which can deliver you guaranteed power supply at the guaranteed energy and the power is what the major requirements for the batteries when we are using for the space and defense applications. And of course, alternate power supplies like nuclear power sources are being used, but it is a very high critical area like we discussed in the nuclear propulsion systems. The safety concerns are always there, and the international agreements and the acceptance, SWOT analysis, and the policy adherences. There are a lot of areas which has to be worked out in this area other than the technicalities. So the power supply systems are also working mostly in reusable using. And if you look at the defense area for the battlefield transparency is what one of the major areas where we need to have the information about the surroundings. We try to look continuously deep into the periphery we're looking for. So the future technologies are to focus on the integration of the information, whatever we could receive through the sensors, what already we have. And third one is that the smart decision-making support mechanisms we have to give it. And we have to give a reliable file-safe data, and we have to give an architecture to get this information, process it, and provide the solution for the end users. The thing is that the adequacy and redundancy, that is to provide a reliable and fail-safe architecture, normally we are look at redundancy has to be provided, and exactly it has to have an improved data handling system so that the compact efficiency can be improved. That is what the basic requirements are. So it calls for integrated platforms to support both voice, data, image, and other multimedia applications and networking also. The indigenization of those current access network hardware is what the next thing is. And real-time solutions is what is to be provided, and the smart radios and software-defined radios are the one thing what we are looking for now. And now the electronic warfare is what one thing for the ground support. If you see that there is an unprecedented growth in the battlefield electronics, so the jamming is one area is a lot of concern, and the same thing, jamming is used as a weapon also, and avoiding the disruption, it every individual wants and every system is looking for. So jamming of other systems and avoiding the disruption for our own system, it is getting complex day by day. It has become a rat race, and everybody tries to outsmart the other one in one area, and subsequently it is going for new innovations and innovations in that area of like. So the unmanned air vehicles with electronic warfare, then wideband signet comet and electronic warfare systems, they have to be developed in near future, being under development also for different nations and throughout the world. The nanomaterials, what we are talking about earlier, that sometime around in 1959, our Richard Feynman, the Nobel laureate, said there is a plenty of room at the bottom. It was one of the game-changing statement actually. What people that time we were working for the major systems and very large systems, they were looking for huge systems. When he said there is a plenty of room at the bottom, suddenly the total concentration moved on to the basic building block of the particle, that is in the nanomaterials. That the nanomaterials research has gone to different disciplines, like be it is electronics or subsequently metal matrix composites, that stealth coatings and the self-shielding materials, you take the camouflage materials, or you take up the electronics or power systems or any major structures, metals, everywhere that nanotechnology or the nanomaterials area it is going to picture, because the products developed through these nanomaterials had been smaller, it has been lighter, and they were able to make it faster, and with the equipment's availability, it is getting a bit cheaper also. And the durability of the systems are really good, and it is you are able to tune to the particular properties what you are looking for. And a lot of instruments developments have happened in the instrumentation side also, that where the nanomaterial technology is improving, like electron microscopes to atomic microscopy to X-ray diffraction methods. Already we had a lot of X-ray diffraction methods in for the quality assessment and the quality control, but with the nanomaterials, the X-ray diffraction method, the procedure and the velocity, everything have improved a lot, and they are going for highly miniaturized reflections, and we are going for the better quality control of this. So a lot of methods are there, and new equipments have come with these nanomaterials, and to test these nanomaterials and the kind of things are too. And in the MEMS and nanotechnology also, as I said earlier, a lot of MEMS equipments have come, right from MEMS sensor to MEMS actuators to your biosensors and rest of the things. And the nanotechnology has given us a lightweight, strong things. And artificial intelligence and machine learning, there's no area which these two things are not touched. So the fuzzy logic earlier we started with the analog instrumentation method, subsequently it went for the PLC. When the process industry was changing from analog controls to the PLC, programmable logic control, there was a huge hue and a cry, and there was an amazing change in technology, where we could feel the changes, where things were happening in what you call electrically connected, hardwired analog control to the programmable logic controllers based digital controls. The change between these two were highly feelable, and it was realistic, and we could see the changes happening. But after the PLC has happened, when people moved to distributed control system like the DCS, and subsequently they went for smart control systems with the CAN network and Profibus and the other things, the changes we could not feel much, but the improvements and the changes were happening in a fast pace. So today, even the rest of the areas also, the initial changes when we moved to digital, it was very huge. But in digital itself, when the delta changes are happening, these happenings we are not able to feel much. But suddenly one day, if you see that what happened 2 years back and what is today, if you see the change in that, it's really very huge. So things are happening without we knowing that there are a lot of changes are happening. So we have to prepare ourselves every day for the every changes in the technology, that how we can do it better, like from photonic or quantum applications, or in the robotics, or in image interpretation, subsequently in the navigation systems. Like today we have got indigenously developed IRNSS. This is going to be of great use in subsequent years, when all that satellites have been launched, and precisely we are going to use it, and the packages are available for the ground. So they will play a lot of roles. So we have to prepare ourselves and equip ourselves to deal with all these things. And similarly, for the defense applications, we have the stealth material and non-lethal weapons. A lot of work is going on. The stealth material has to be, what do you call that, the stealth capability against normal vision and IR vision and other scanning techniques we have to defend. The more and more we are looking for seeking technology, the more and more other side that to prevent that seekers, we have to work on these stealth technologies. And for the non-lethal weapons in the urban areas, we have to go for the stun grenades or the optical weapons and the acoustic weapons. These are the major weapons what we have. Things are already working on. Work is being carried out by different agencies throughout the world in these areas, and being used also. And in the label systems, we are looking at shafting and the controllable pitch propellers. And there are non-magnetic engines are used for minesweeping vessels, and the better zero maintenance batteries, where it can have a lot of duration, is more important for the naval systems, and automated power management systems for the ships. And the major requirement what is happening is, even if the technology is already available, how to make it to suit the special requirements what we have in the present day scenario and the present requirement. Similarly, in the manufacturing process also, The metal forming process, normally we used to roll a big piece of metal and roll it and have a welding and rest of the things. Now that stretch forming has come, and the huge vessels, sheet metals and tubes are being made with the stretch forming. Subsequently, the flow forming methods have come into the inner barrel of the wheel, like where the stresses are created to give the aluminium. And these sort of materials, and we are forming systems with the forging process earlier it was used. Now the flow forming has come. The 3D printing, of course, the 3D printing is available in the market using normal plastics and other sort of things now with the direct metal laser sintering and the selective laser sintering. The metals or metal models are being used using the 3D printing, and the selective laser belting is also happening. These are the things what we are looking at the manufacturing process. And the surface finishing, normally now we are looking at 1.6 microns are expected for the job. It is a very high precision job. Now high-end CNC machines with 6-dimensional CNC machines have come into picture, and we are able to even reach at 1 microns of surface finish. Now the industry is moving on to industry 4.0. Earlier in industry 1, it was purely a manual one. Now industry 4.0, we have gone into IoT-based manufacturing industries. With all these things, the developments, whatever the technology and other things you are doing, but ultimately it is quality control and the quality assurance, and how the non-destructively does the equipment, like the dye penetrant test for the mechanical properties, the ultrasonic test, the radiographic test, and the acoustic emission test, and subsequently the power on EMI EMC test, and you have what do you call, normally you take the PCBs and put onto thermal cycling and see that whether it is giving up, how far it is working. Individual component wise, how to go for the quality control, and subsequently as you make a system, how to go for the quality control, and making integrated into a major module, how the performance has to be verified and how the regularization has to be confirmed. So basically the structural integrity, structural and integrity evaluation of the system what we are making, the aging studies, how it is going to perform in another 10 years, then the prediction of the failure in what are the ways it can fail and how it can be muted, the reliability of the system, that what confidence we can give it to the end users, and subsequently the preventive and the predictive maintenance, at what range. About you are using a rubber component, okay, it will go for a life of 5 years, 10 years, 12 years. How to predict the aging of those systems and introduce a system to work on that so that it can be replaced and things can be improved. So these are in the quality control, and the quality functions for the field is how can be fed back into the process system where the quality can be controlled right from the beginning of the process itself. So like I said, quality at the component level, then in-process quality, and the quality at the subsystem level. This is what the quality planning is. And a lot of effort is happening, as I said that twice earlier, that you have to be first and right. If you don't have a second chance for both on space and defense technologies, in that case, the rigorous quality control regime is on, and the philosophy of quality control and the quality assurance philosophies are being updated every day based on the inputs, whatever the experiences we had and what we are experiencing now. So the need of the product, what is happening is, normally we say that necessity is the father of the invention. So, but what happens is the scarcity is the mother of innovation. We have the technologies already available, we have the systems are available, but only the thing is that we have to innovate how to make it with available materials and available technology so that the best product can be made. Like I said in the first slide, we have to provide the best possible solutions with the available material and available technology. And this research, it don't have any boundaries. It is going to be the ultimate. And but I've seen a lot of fiction movies and the cartoon shows what we are seeing on the televisions and all. We can take an example of the Contagion movie, what happened somewhere in 2013 or 12. And today, that movie, we are seeing it today, what is happening in the world. And there are a lot of movies, what you have seen earlier in the Hollywood movies and other things, or if you take a lot of the cartoon shows. So there is a mind which is working that what can be in the future, what can happen in the future, and how things can be perceived and how it may work also. Today, what we say is a fiction. Some years down the line, it is going to be an actual event, and they are going to be a reality, and we cannot omit anything that just it is like that. Just everybody has told, and it may not happen. We have to think as an engineer that is it possible that it may happen. If it happens, how it is going to happen, how to do it or not to do it, how to prevent it. These are the things that we work on. And if you look at the aspirations and the aim of our Indian this thing, if you look at the NITI Aayog's technology innovation brochure, India need to be among the top 50 countries in the Global Innovation Index by 2022 and 23. And 5 of our scientific research institutions should be among the top 100 in the world. And we are trying to spend at least 2% of our GDP in R&D with equal contributions from both the government and the private sectors. But the fact is, in India, we have 218 R&D professionals compared to China's 1,113 and the USA's 4,019. And a major one observation what Niti Aayog has made is the link between the research, higher education, and the industry is weak and nascent. It needs to be strengthened and put on a firm platform. Lab to land time is too long, and hopefully all the academic people and the industry people are listening. That this gap is what we have to reduce, and so that time to market can be reduced, and the available technology and the knowledge can be shared, and better final products can be made for us to consume. And of course, government has taken a lot of policy progress over the years. In 1971, we had the Department of Science and Technology, and 2016, the Digital Innovation Mission has been launched. A lot of things are happening, and we have skill development programs, and a lot of things are happening. Of course, you know all the present happenings as of today. It is well publicized in all the medias and newspapers. So availability, opportunities are available, knowledge is available. And as and more the skills are developing, we need more acharyas also. So we have to increase our knowledge in both the teaching, not only in making engineering happening, and in spreading those engineering knowledge also. So with this, imagination is what is important. So what we do for all these things is what we call it as to without making any product, whatever we have, the knowledge is available, whatever the resources available, we need to go for system engineering. Ultimately boils down to that system engineering. System engineering, if you see, it is basically the integration of the complex systems, taking into account the safety, cost, schedule, reliability, and everything. We have to put into a system, and we have to take the input. We have to say how output is required and how the system is going to make it, and we are going to test it, and subsequently how we are going to deliver it. The system engineering, initially it started in the space industry, subsequently in aerospace, and we are using in the defense also. But ultimately now system engineering is used in every walk of life and in every engineering disciplines, actually, for every product and every design. And as per the Greenpeace critical behavior of system engineering, we have with the intellectual curiosity, he has defined that what are the behavioral characteristics of a good system engineer and how a good system can be made. So at the last, what happens is with all the technologies and whatever we have with the National Academy of Engineering, it has listed out a few of the challenges for this century. It is making solar power economical, providing energy from fusion, developing carbon sequestration methods, and managing the nitrogen cycle for the environment, providing access to clean water, restoring and improving urban infrastructure. Of course, things are happening every day. The advancing the health informatics, engineering better medicines. Anyway, we are in the crux of that today. And reverse engineering of the brain, and preventing nuclear terror, and securing the cyberspace, enhancing the virtual reality, and advancing the personalized training, and engineering the tools of scientific discovery. So these are the major challenges what we can put across with all the available technologies today, which is of more use to the common man and the society per se. With this, we have just had a small beginning about what is happening around, and as I said in the first training, I have just shared whatever I could learn and hear and grasp from my environment, and it is not a complete, it is only the beginning what I will give an introduction about what is happening around. Clarity is left out, and all the concerned and interested can take up, and if any some more things are required, you please contact me. With this, I thank you all. I thank the organizers. I thank the participants, and I thank you all for this patience hearing. Thank you very much.
Thank you very much, sir. Thank you.
Thank you, sir. I would like to thank our chief guest, Mr. Srinivasan, sir, DRDO, who enlightened the participants and also us. From this, we learned earlier engineering, then different space sectors like launch platform, ground support systems, and satellite communications, and solid propulsion systems. And I would like to thank our correspondent sir, principal sir, and Mohan Babu sir, mechanical, HOD, then faculties of ECE and head of the various departments and faculty members and participants. Once again, I would like to convey my heartfelt thanks. Thank you all.
Participants are requested to fill up the feedback form.
Hello. Yes, I would request the participants to fill the feedback forms.
The feedback form link will be posted in the chat box.
Participants are requested to fill the feedback form. Then only we can be able to provide the certificate. Kindly fill the feedback form.
Sir, shall we conclude now?
Yes, sir, we will conclude.
Okay, sir. Shall I close?
Yes, sir.
Okay, sir. Thank you.
Please proceed. Thank you all. Once again, I would like to thank all the participants. Thank you.